Right, hello everybody. Welcome to the National Tutoring Campaign, and this is a grade 10 physical sciences lesson. My name is Clinton van der Venter, and I am excited to be going through some important science concepts with you today. Today we're going to be working on some term 3 chemistry, and we are now diving into a section that students often find difficult. And that is what's called quantitative aspects of chemical change. Okay, your teachers might call it stoichiometry, big fancy word. It just means that we're going to be doing a lot of calculations around a chemical reaction. So let's get going. I first of all want to touch on some things that you should already know from term 1 work. Okay, and these are the substances that particles are made up of. And here are 1, 2, 3, 4 examples. Okay, these are the main examples that you should know. Diamond is an atomic substance because it's made from atoms. Okay, so we call a substance that's made just from atoms atomic. And diamond, as you should know, is carbon. Okay. The element symbol for carbon is C. Carbon dioxide is a molecular substance because it is made from molecules. So carbon dioxide comes from CO2 molecules. Sodium chloride is an ionic crystal lattice, and it's made from ions. Okay, sodium chloride is salt that you put on your food, and it's lots of different types of salts. But we call it ionic crystal lattice because it's made from positive and negative ions. And then gold. Gold is a metallic substance. Okay, so metals are in a separate category, all different types, all the metals, zinc or magnesium or calcium. They are made from positive metal atoms in a sea of delocalized electrons. So that's what substances are made up of. They're either made up of atoms, or molecules, or ions, or from atoms in a sea of delocalized electrons. Sodium chloride is NaCl, and gold is AU. Right. A molecule or a compound, it's important that you understand the difference before we go on to the hard calculations. We know that one molecule or compound has a substance has a certain atomic ratio. For example, carbon dioxide, CO2. That little 2 there means that for every 1 carbon, there are 2 oxygen atoms. And in this picture, we can see a molecule. Okay, that's the water molecule, H2O. It means there's 2 hydrogens for every 1 oxygen. And here is what we would call a compound. This is magnesium hydroxide. And you can see by these charges that it's made up of ions. Okay, so if something is made up of non-metals, we normally call it a molecule. And if it's made up of a metal and a non-metal, then we call it a compound. We don't really call it a molecule. Okay, and that compound is made up of ions. Okay, so if it's ionic, it's a compound, and if it's a non-metal or covalent, then it's a molecule. Right, you also would have been exposed to this in about term 1, relative molecular or formula mass. And this is really, really, really important that you understand how to work out the relative molecular or formula mass. The mass of one molecule or formula unit of a substance. Okay, that's what it is. We already know that the relative atomic masses of atoms are found in the periodic table as the mass number. And when we are working out the molecular or formula mass, we simply calculate it by adding the atomic masses. So let me go to the periodic table to show you. Okay, this is the one that you would get for school. This is what would be in the documents, in the subject guideline documents. So this is the key here. And it tells us that this top number is the atomic number. That is the number of protons of an element or an atom. And the bottom number, this is the number that's important for what we're talking about today. This is what we call the relative atomic mass. Sometimes you might hear atomic weight, but we should rather use the term atomic mass, okay? And that's the mass of that atom, okay? And it's measured in atomic mass units, and we're going to clarify that a little bit later on in the lesson. But when we are working out the relative molecular or formula mass of a molecule or a compound, then we are looking at the bottom numbers on the periodic table. So for example, carbon dioxide, how would we work out the molecular mass of that? I would look at carbon and I would look at the mass. It's 12, okay? So it's 12 plus, now I need oxygen, O2, there's O2 there. So I'm going to go and I'm going to look for oxygen. The relative atomic mass is 16, but now I need to have 2 times 16 because of the formula. It has 2 oxygens in it, okay? And if you type that into your calculator, it is going to do your body mass automatically, but it's good for you to be aware of it, okay? 12 plus 2 times 16 gives you 44. So that's the relative atomic or relative molecular mass of carbon dioxide. That's how we work it out. And for example, NaCl, okay, now we won't call it relative molecular mass, we'll call it the relative compound mass or the formula mass, because remember, this is now not really classified as a molecule, this is classified as a compound, and often we just use the word formula. Okay, so we look for Na, and we see that the mass is 23. There's only one Na in the formula, and then we look for Cl, and we see that the mass is 35.5. So we add those up together, and that would be the relative formula mass of sodium chloride, 58.5. And I'll talk about units just now. So I hope that was a good reminder for you. That's how we calculate. So if it's a molecular substance, we just call it molecular mass. And if it's an ionic substance, then we call it formula mass. They essentially are kind of the same thing. We just use the terms differently when we're distinguishing between a molecule or a compound. Right. Determine the molecular or formula mass of these substances. So it will be handy to have a periodic table out in front of you. I've got H2SO4, so I'll walk you through it quickly. We're going to go to our periodic table. Now we've got H's, H2SO4. So the atomic mass of H is 1, and then S, that's sulfur, is 32, and O is 16. So it's 1, 16, and 32. Remember that when we're working it out. Now we're going to have 2 hydrogens, so it's 2 times 1. Then we have 1 sulfur, which is 32. Okay, we're getting it from the periodic table. And then we're adding it to our 4 oxygens. Okay, I ran out of a bit of space there. 4 oxygens. And now I'm going to add that all up on my calculator, and I get 98. Okay. So what I'm trying to point out to you here is your subscripts, and make sure that you take them into account when you're calculating the molecular or formula mass. So you would be able to say that this is molecular mass because all of those elements there are non-metals. Okay, this one, the next one would be, we would be working out the formula mass, which is the correct technical term because it's made from zinc and CN, cyanide, iron, and that is a metal and a non-metal. So technically we would call it formula mass, but the way we work it out is exactly the same, okay, as we would do for molecular mass. So we're going to go to our calculator, we're going to look for zinc, Zn, we're going to look for C, and we're going to look for M. Okay, all of those different elements on our periodic table. Zinc is over here. It has a formula mass of 65. Carbon has a formula mass of 12, and N has a formula mass of 14. So that's where I'm getting the numbers from. Now we're going to work it out. And now look at this formula. It's a little bit complicated. There's Zn and there's brackets with the Cn. So that means there's two C's and there's two N's. Okay. So when I'm working out my zinc, I have 65, only one 65. But then I have two, well, I could do it like this if you want. Carbon is 12 and nitrogen is 14. But I have two of those things because those carbon and nitrogen are in the bracket and there's two of them. That's what this little 2 here means, that there's two brackets of Cn. So hence the way I'm working it out here, 65 plus 12 plus 14 times 2. So remember our bod mass here, we always multiply before we add. Your calculator, if it's a scientific calculator, will do that automatically though. So that's 117. And then let's look at another one. Aluminium oxide. This would also, we would call it formula. We'd be working out the formula mass because aluminium is a metal, oxygen is a non-metal. So let's go back. We've got aluminium and oxygen. Let's go back and look at our periodic table. Aluminium, it's always handy to have your periodic table close to you when you're doing chemistry so that you can always, need to refer to our atomic numbers or mass numbers. So aluminium has a mass of 27 and oxygen has a mass of 16. So let's work it out. Now this time I've got two aluminiums. So it's 27 times 2 plus, then I've got oxygen, which is 16, but then there must be 3 of them because there's 3 of them in the formula. 3 oxygens, 2 aluminiums. Work that out with my calculator, and it should get 102. And that's how we work out the molecular or formula mass. So now to introduce you to some new concepts which you need in order to continue with these calculations. The mole concept. Okay, now we're not talking about a mole that digs holes in the ground. A mole is a quantity in chemistry. Just like in maybe everyday life, we use the term a dozen. If your mom tells you to go buy a dozen rolls from the shop or collect a dozen eggs from the next door neighbor, then what does she mean? She means that she wants 12. So it's a very similar concept, except in chemistry, a mole doesn't mean 12. A mole means 6,02 times 10 to the power of 23 of those things, which is a lot of things. Look at this number here. I've got it on the next slide. I'll show you. Okay, it's a big, big number. There's no decimals in it. Okay, even though it says 6,02, if you had to write the number out, that's what it looks like. 602 sextillions, 200 quintillions, quadrillions, trillions, billions, millions. So it's a very, very big number. There's a lot of, yeah, that's a lot. It's hard to understand that. But it's the same concept as a dozen. If we're talking about a dozen, we need 12. But if we're talking about a mole, then we're meaning 6,02 times 10 to the power of 23. And we rather say 6,02 times 10 to the power of 23. It's just easier than to say 602 sextillions, quintillions, quadrillions, trillions, billions, millions. You can see that will take a bit too much time. So the symbol and this number is called Avogadro's number. Not avocado, Avogadro's number. And it has a symbol N with a little a. Okay? So if you see that, it means we're talking about Avogadro's number. This number is given to you on your formula sheet when you write an exam or something like that. So you don't have to learn it off by heart. It's given to you, just like the periodic table is given to you. So here's a nice, just an example. 1 dozen would mean 12, say, eggs. 1 gross, I don't know if you knew this, 1 gross means 144 eggs. 1 million, that's also like, if I had to talk about a million or 100, you know what I'm talking about. 1 million is 1 million eggs, and 1 mole would be 6,02 times 10 to the power of 23 eggs. Okay, so we're talking about a real lot of eggs. So that's a new concept. A mole, if we're talking about a mole, 1 mole is a certain amount of substance. And it means that there is 6,02 times 10 to the power of 23 things of those substance. The unit for mole is MOL. Okay, without the E, that's just the unit. Like we have kg for mass, or meter, M for meters, like lengths. Mole is what we use as our unit. And we'll get there as soon as we start practicing some calculations. Right, so molar mass M is the mass of 1 mole of substance measured in grams per mole. It is the same as the relative molecular or formula mass. So this is a new concept, but it's something you already know how to do, thank goodness. Okay, so the molar mass is a term we use, molar. So molar comes from the word mole, okay? It's the mass of 1 mole. That's why we have the term molar mass. The symbol for that is just a capital M, okay? It's the mass of 1 mole of substance, and it is the same as the relative molecular or formula mass. So as we worked out, the relative molecular mass of carbon dioxide was 44, okay? That is also called, it's called the relative molecular mass, but it's also called the molar mass. Okay, so now we're just linking this to the concept that I revised a few slides ago. And now we're going to have a unit, and we're going to say 44 grams per mole, because that's what molar mass is. It's the mass per mole. So that line means divide per grams per. Okay, and then we did, what else did we have? We had H2SO4, which was 98. Okay, so now that's the relative molecular mass of H2SO4, but now we can say that's also the molar mass. So we know that 1 mole of H2SO4 is 98 grams. 98 grams per mole. Okay. If I had 1 mole of carbon dioxide, that means if I had 6,02 times 10 to the power of 23 molecules of carbon dioxide, the mass of that would be 44 grams. And if I had 1 mole of H2SO4, that means I have 6,02 times 10 to the power of 3 molecules of H2SO4, it would have a mass of 98 grams. Okay. That's what molar mass is. It's the mass of 1 mole of something. So if I had 1 mole of gold, okay, like gold as in the metal, if I had 1 mole of it, it means that I have 6,02 times 10 to the power of 23 atoms of that element. And if we look on the periodic table, look for gold, how much would that mass be? It would be 197 grams. Okay, that's would be 1 mole of gold, 197 grams. Okay, so now we know about the mole concept, okay? It's the amount of substance, that big number. Now we know about molar mass, okay? It's the mass of 1 mole. Now we can start to calculate the number of moles in a certain amount of substance that we have. And we're going to use this formula. N is equal to little m divided by big M, okay? And what does that mean, okay? N stands for the number of moles. It's in this triangle, which is helpful to use. Little m stands for the mass of whatever we have. And then the big M stands for the molar mass of whatever that substance is. So say, for example, I have 20 grams of gold. Okay, you steal your mother's ring and you melt it down and you see that it's 20 grams of gold, okay, which isn't very much. So how many moles is that? Well, you could use this formula to work it out. You could say, well, N is the number of moles. It's equal to the mass divided by the molar mass. So what is the mass of the gold that I have? The mass of the gold is 20. And what is the molar mass of gold? And you always get that from the periodic table like we did just now, 197. The molar mass of gold is 197. So the M is always available to you on the periodic table, this big M. It's always available on the periodic table. And then you work it out, 20 divided by 197, and that is 0.1, if we just round off to 1 decimal, 0.1 moles. So if I have, and there's my little unit, okay, MOL, we don't put the E on the end, 0.1 moles. That means I don't have 1 mole of, I don't yet have 1 mole of gold, I only have 0.1 moles of gold. Okay, and that's how that equation works. And we're going to be using this a lot and a lot and a lot. So you're going to get used to it quite quickly and quite easily. And I don't know if you all know how the triangle works. You will be given this formula in your formula sheet. But if you remember the triangle, then if you are asked to work out moles, then it's small m divided by big M. But if you are asked to work out small m, so the mass, then you're going to say it's the number of moles times the molar mass. That's how it works. Okay, and we'll work on that now as we go through some examples. So here is an example. How many moles are there in 50 grams of copper chloride, CuCl2? How many moles? So they are asking us to work out N. N is how many moles? Okay, referring back to this formula. So I always find it helpful that you write down your formula. N is equal to M divided by N. Okay, small n's might be helpful for you to distinguish between small m and big capital M. Okay, mole mass divided by molar mass. So what is the mass of copper chloride that we have? It is 50, okay, 50 grams. So this M they have to give to you in the question, the small m. Now we've got to figure out the molar mass of copper chloride. So that's why I spent time in the beginning of this lesson making sure we know how to do that. So now we've got to work that out. We don't have to work it out separately. We can just put it in our formula. But let's quickly get the relative atomic masses of copper and chlorine. So we go to our periodic table, you go to copper, here it is. Okay, the relative atomic mass is 63.5, and then chlorine is 35.5. And as you do this, you'll get used to these numbers, and some of them you'll know off by heart. So now we can go back and work it out. So I like to just put it in brackets instead of working it out separately. Copper, we've only got 1 copper according to the formula. I'm looking at this formula here. There's 1 copper, so that was 63.5. And then now I have to add it to 2 chlorines. 2 times 35. 35,5. Okay, and then I just type that into my calculator. Or you can work out the bottom first if you want. You can work that out and then divide it. But remember, you don't want to round off until the very end. And that's a skill that you need to learn as you are in maths and for science, that you shouldn't round off until the very end. So I like to just put it all into my calculator. So you can use brackets on your calculator. And it gives you the answer, and then you only have to round it off. So you get 0.37. If I go to 2 decimal places, and it's going to be 0.37 moles. Now we say moles, but it's just written as MOL. without an S. Okay, so that's how we work out the number of moles. Now this question, the next question is a little bit different. We're going to use the formula in a different way. What will the mass of 2.5 moles of NaClB? So imagine salt in your cupboard. Okay, if you've got 2.5 moles of that, then what is going to be the mass? So now you're going to go back to our formula, and we need to change that subject of the formula so that we can work out. Now we don't want to work out N because we've already got N. Big M we can always get from the periodic table. We now need to work out little m, okay, which is this one. So that's why if we learn our triangle, then mass is now equal to moles times molar mass. Helps us change the subject of the formula, nice and easy. So I like to write it down. Mass is equal to the number of moles times the molar mass. So they gave us the number of moles in the question. There's 2.5 moles. And then we need to times by the molar mass, which we got to work out from the periodic table. And we did do that one in the beginning. NaCl, let's quickly, I rubbed it out already, but Na is 23 and Cl is 35,5. So if we just add them together, put them in brackets, then our calculator will know what to do. Now remember, you're adding them, you're not timesing them. Let me make that a bit clearer there. Okay, so it's going to be 2.5 times 23 plus 35,5, and I get 146,25. And now what am I working out? Mass. I'm working out the mass. And what is mass measured in? Grams. So remember to put my correct unit, otherwise my answer won't make any sense. Okay, so if I have 2.5 moles of sodium chloride, then it is 146 grams. Okay, comma something grams, 146 grams. Which you think about a chocolate, what is a chocolate is about 80 grams. Okay, so it's a little bit more than how heavy a chocolate feels. So there we go. There's an example, 2 examples on using the formula. Now let's try this next one. This is another way that a question could be asked to you. I have 65 grams of copper 2 sulfate. Now remember, this is our Roman numeral notation. So now they've made it a bit harder because they haven't given us the formula, and we need to know the formula in order to work out the molar mass, the big capital M. Okay, it says calculate the number of moles present. So in order to do that, okay, see, this is where I need more space. In order to work out the number of moles, it's mass divided by molar mass. Now I know what the mass is, it's 65 kgs, but the molar mass is now going to be a little bit trickier because they didn't give me the formula. They just said copper 2 sulfate. Now, a lot of students go, oh, that means copper 2 sulfate. And that is not what Roman numeral notation means. So if you had to write down the formula like this, it's wrong. And then you're going to work out your formula, your formula mass or your molar mass incorrectly because you're going to think there's 2 coppers. And yeah, you're going to think there's 2 coppers, and that's incorrect. So what does Roman numeral mean? And this is just a nice recap. You learn this in term 1. Roman numeral means that the valency of copper in this case is 2. It's plus 2. Remember, copper in the periodic table is a transitional metal. It's in that middle bit here. And it doesn't have a valency. Remember, this is +1, and this is +2, and this is +3, etc. And this is -1, and this is -2, and this is -3, and this is plus and -4. So when we're looking for the valency of copper, we actually don't know what it is because it's in this middle bit, and it means that the valency changes depending on the circumstance for all of these elements here. The valency could be +1, it could be +2, it could be +3 in some instances. but they have told us in this Roman numeral notation that it's copper 2 sulfate. So that means that it's copper 2 plus. Okay, copper's a metal, so it will always be 2 plus. None of those elements will ever be a minus because they're all metals, and metals will always lose electrons and become positive ions. Now, sulfate is one of those compound ions, and you need to know off by heart that sulfate is SO4 2 minus. Okay, and if you look in any textbook available to you, a list of the compound ions will be there, and I did talk about it last week or the week before. So how do I write the formula for copper 2 plus and sulfate 2 minus? Well, remember our little rule, we bring the 2 down there and the other 2 down there, we do a little crisscross. And that means that we're going to have copper 2 sulfate 2, but we always write the simplest ratio. So if I have 2 to 2, then it can be simplified as 1 to 1. So when I'm actually doing the formula, I don't write copper 2 sulfate 2, I just write copper sulfate. So that's the formula. Okay, so that's what makes this question just a little bit more tricky, because you've got to come up with this all on your own. So you need to know what this Roman numeral notation stands for. And it doesn't stand for copper 2 sulfate. That would be incorrect. Okay, that's wrong. Okay, now we know what the formula is. Now we can work out everything we need to work out. Remember, I'm actually working out the number of moles. Okay, so all that thinking before we even start the question. Number of moles is mass, which is 65, divided by molar mass. So now I need the formula of copper sulfate. Copper, 1 sulfur, and 4 oxygens. So copper is 63.5, sulfur is plus 32. Let me put it there. I won't keep referring to the periodic table, just so that we have enough time to get through the nitty-gritty stuff. And then there's 4 oxygens. Oxygen is 16. And now remember this little bit. You don't have a scientific calculator, you must do it first. And if you times that all in, if you type that all into your calculator, you're going to get 0.4, and if we round off to 2 decimal places, 41 moles. We only write MOL. So it's not even 1 mole. Okay, if I have 65 grams of copper sulfate, it's not even 1 mole. It's all 4 moles. Okay. What is the meaning of the above answer? Okay, this is a bit of an open-ended question, but it's there probing to see whether you understand sort of the mole concept, because it's important. So what does that mean? It means if I have 0.4 moles of something, then it means that I have, bear with me here, 0.41 times 6,02 times 10 to the power of 23 particles of that thing. Okay, so remember 1 mole is 6,02 times 10 to the power of 23. So I don't have 1 mole, I've got 0.4 moles. So how do I get that amount? I have to times that 6,02 by 0.41. So that is 2,4. Let's round off to 1 decimal place. 7 times 10 to the power of 23. And we're going to say formula units. That just means we're not going to say molecules, because remember copper sulfate, it won't be a molecule because it's a metal and a non-metal. So we will just say formula units. All right. So that's what it means. And yes, they didn't ask you to calculate anything, but they're just asking to see if you understand what this whole thing, that this number of moles means. If I've got 0.41 moles, then I don't quite have 6,02 times 10 to the power of 23 of those things. I just have 2,47 times 10 to the power of 23 of those things. Sorry, guys, big words. Hey, scientific notation. Thank goodness we use scientific notation. Otherwise, imagine we had to write out that big number. Okay, and then this is a question that they love to ask. Calculate the number of oxygen atoms in the 65 grams of copper 2 sulfate. So, remember we've got 0.41 moles of copper sulfate. Okay, that's what we worked out in question 1, 0.41. Let's write it here so we don't have to keep switching. Okay, calculate the number of oxygen atoms. So now we already said, because we've got 0.41 moles, we've already said that we've got 2,47 times 10 to the power of 23 formula units. But now look at the formula for copper sulfate. Okay, for every 1 copper and 1 sulfur, we have 4 oxygens. So how many oxygen atoms is this really? Okay, so, well, it's 2,47 times 10 to the power of 23 copper atoms. It's 2,47 times 10 to the power of 23 sulfur atoms, but it's 2,47 times 10 to the power of 23 times 4 oxygen atoms, because for every one of the copper or sulfur, there is 4 oxygens. So what do we have to do? We have to times that 2,47 times 10 to the power of 23 by 4. And it's 9,8. Let me round off just to keep it simple. We don't want to grapple here with numbers necessarily. We want to understand the scientific concepts. It will be 9,9 times 10 to the power of 23 atoms of oxygen. Okay, so I hope that makes some sense to you. That's a kind of question that they love. So when you're practicing, make sure that you can identify those kind of questions and maybe come back to this video and have a watch of how it is done. Right, we've got 3 more minutes, so let me quickly touch on empirical formula. So this is a big fancy word, but all it means, it's the simplest whole number ratio of elements making up a compound. So we already spoke in the last example. If I had Cu2SO42, that's not the simplest ratio. We'd rather have CuSO4 because 2 to 2 is the same as having 1 to 1. So when it's not the simplest ratio, it's called the molecular formula. So like P4O10. And when it is the simplest ratio, because 2 can go into 4 and into 10, so we can simplify just like you would simplify a fraction, then the empirical formula is P2O5. And you can look at these other examples. C10H22, the most simplest formula would be C5H11 because 2 can go into both 10 and 22. Same thing with this one, C6H18O3. What can go into all of those? 3. Okay, 3 can go into 6 twice, into 18 6 times, and into 3 once. So then we get a nice simple empirical formula, okay, of the atoms within that formula. So when I begin next week, we will continue with these. There's lots of calculations involving the mole concept. Okay, so this was the main point of today's lesson, is to understand the mole concept and to understand there's the mole concept and to understand how to work out the number of moles. And there's lots of ways that we apply this concept going forward. So guys, that's all I'll talk about today. There's lots of stoichiometric calculations to come, and I'm excited to walk through that with you, because it can get quite tricky if you're on your own. But guys, I just wanted to encourage you, hey, science is all about problem solving. That's the way I see it. Without science, we wouldn't be able to solve our problems. And, you know, you might be grappling with the work. It might be difficult. You might not understand certain concepts. You might get sent home with homework and not know what to do, even though the teacher just explained it to you. That's okay. That's all right. And it's all right to feel frustrated and disappointed about that. But what are you doing about those feelings? Science is about facing our problems and then coming up with a solution. Okay, your problem is you don't understand how to do the homework. Well, what are your next steps? Okay, what can you clarify? Can you go back? Can you summarize? See what works for you. Is there somebody you can talk to? Is there a video that you can go and watch? Because we all are capable of solving these problems. I did my whole Bachelor of Science degree through correspondence. I didn't have anyone teaching me how to do it. And from that experience, it taught me so much that you really can learn anything you want to, as long as you put your mind to doing it. Okay, you don't always have to get somebody to tell it to you the whole time. If you really want to find out about how to do something, you actually can go and figure that out. And that is the scientific process. Any problem that people have faced in their lives is all being solved, and whether we know it or whether we understand it or not, through following the steps of that scientific method. What is the problem? Ask the question, how can I get it solved? Maybe this will help, maybe that will help. And then you try it out and you see if it does work. And if it doesn't work, well, then you start again. Okay. So, oh, I did bad for my chemistry test. Well, maybe I should go for an extra lesson. Does it help? Okay. Then if it doesn't help, what else are you doing? Remember, you've got to give things time. Maybe one extra lesson is not going to help you. Maybe you need to be strict about doing extra lessons for a whole term or whatever it is. But persevere, because that's what science is all about. You're not meant to be born knowing all of this stuff. It takes hard work. But if you spend the time going through the textbooks and maybe doing a bit of research on the internet, you will find that lots of people are grappling through this, and there's lots of excellent explanations for some of these concepts. And once you unlock that idea of knowing that you can actually figure anything out for yourself on your own, it's going to just open up your whole, the whole trajectory of your education for the future. So good luck, guys, and yeah, we'll see you next week. I hope that you get to practice some of this. If you go look at any textbook that you might have on physical sciences, this is called Quantitative Aspects of Chemical Change. So the chapter might be called Chemical Change. It might be called Quantitative Aspects of Chemical Change, but look for the mole concept, and you will be able to then find this work. And we haven't touched on everything today. We still need to do lots of different types of calculations, but you can start working so long on anything that you might pick up there. And please remember, let me find my end slide. See, I plan to do a little bit extra today. If you need anything or any resources, please may you email me at clint@africateamgeeks.co.za. And it was really nice to spend the morning with you guys. So thank you very much.